Today we are continuing Unit 6 with the topic of competition of economic aspects. Regarding this, we have seen lightning, and regarding this lightning, various types of schemes we have seen in the last class. So, whenever the lighting source is kept perpendicular to this horizontal axis, when the light source is suspended and the light beam is inclined with certain angle, and regarding this case, how to calculate the total luminance required. And regarding this case, we have continued our problem. Further calculation of number of lamps required for a lighting up of a particular specified area, and the arrangement of the lamps, how to be kept, x-axis coordinates and y-axis coordinates. Regarding these two, how much is the gap you have to maintain between any two lamps in x and y coordinates. So after that, we have seen, so being a topic of energy audit and economic issues, we are going to consider within this energy audit and conservation title. And because we are utilizing light energy for after 6 p.m. up to 10 p.m. or up to 12 p.m. like that, we will use artificial lighting, which was generated by utilization of electrical energy. So till the availability of the sun, there is no need of switching on any electrical lamps unless it is desired. But evening 6 p.m. onwards, we are going to definitely switch on electrical lights. So regarding this case, here there is much scope for us to calculate savings of electrical lamps utilization in the area of power. Now regarding this case, the existing lamps which are highly rated, so that nowadays technology availability, so that we are going to replace all the existing lighting system with a new lighting system which is going to consume very less amount of power. So that the power requirement is getting reduced, the load on the power generation is getting reduced. So the reserves of the coal as well as the water and so on, so they are going to be retaining, they will be extended for some more years. Regarding this case, we have selected the topic of saving of electrical energy regarding these lighting aspects. After that, we will see applications of life cycle costing analysis. Then we will conclude this unit 6 with the return on investment. Now, coming to this issue, here first of all, we will see what is meant by light saving. So, regarding this case, let us see regarding light percentage of total electrical energy was shown within this pie chart. Now, here coming to this dark blue, it is showing the percentage utilization of lighting energy for offices. Then this maroon color is indicating light energy used for retail issues, and others they are occupying with this green. And purple it is showing the lighting energy required for these educational institutions. Then this olive green, so this chrome green is indicating healthcare units, they are placing light energy. Then orange it is showing power consumption that was taking place in case of large units. So like that, different sectors they are utilizing light energy after the natural light, that is light liberated from the sun is absent after 6 p.m. like that. Now regarding this case, here we will see something introduction regarding this lighting issues. So lighting is an essential part of everyday life. So we have to complete our works during the presence of the light. If natural light is not available, we have to definitely depend upon the artificial light. So within this case, definitely we have to look at even though the lights which are provided within a room, they have to specifically provide the required level of illumination. So like that we are seeing, suppose a large room is there, there we are calculating how many number of lamps are being kept, so that the required illumination level is going to be maintained, so that our human eye it is not going to feel any stress or glare regarding this up and downs of illumination levels. So regarding this particular issues, if anything changing, suppose there is a room which is having a dim lighting, definitely we are going to feel some irritation. And if there exists a more illumination within a room, there we are going to feel some, the human eye is going to having some inconvenience to do some works. So all these things psychologically they are affecting the mindset of a human being. So definitely we have to maintain a proper illumination within the workspace. Now coming back to this particular issue, the present scenario is going to show and efficient lighting with the proper techniques are used, a major energy saving is possible. So olden days technology, simply we are using filament lamps, and that is also being circulated with some current. There we are going to have some loss psi square into R, so that is appearing in the form of light. So this is happening in case of function filament lamps. Now coming to this other olden days filament lamps, there is other olden days lamps available are fluorescent tubes, mercury vapor lamps, sodium vapor lamp, and likewise we have seen traction filament lamps, fluorescent tubes. In all those things they are consuming more amount of power, and power loss is also more. So nowadays we are having LED technology that is based on semiconductor devices. Now they are consuming less amount of power. The temperature produced is also being less. In some cases, we have seen the energy utilization by this compact fluorescent lamp, the CFL lamp, that is going to give more amount of light, 90%, and only 10% energy it is going to be generated as heat. Suppose coming to this tungsten filament lamp, that is giving 90%, up to 40% of the energy is getting wastage in the form of heat. Only we are going to have 60% of energy that is converted into light. Now, present scenario, all the existing lamps are to be replaced. Now, coming to this cost parameter, we are going to consider, even though these CFL lamps and nowadays technology lamps are going to be costed somewhat high, either the technology point of view, either the availability. Now, it is one-time investment or capital cost we are going to keep. But coming to this running cost or operating cost, definitely they are consuming less amount of power. So they are going to give less amount of electricity bill. So that initial investment may be appearing as high, but the running costs and everything they are going to be reduced. So that's why it is always better to replace the existing filament lamps or fluorescent tubes with CFL lamps. Now coming to this particular case, there we are having different types of lighting schemes. That is a direct lighting, indirect lighting, semi-direct lighting, direct or indirect lighting. So all these categories we have discussed in our illumination topic. And different types of lamps available. There are incandescent lamps, that is GLS lamps, fluorescent lamps, that is FL, the T12 and T5 lamps. Then we are having, so here we are calling these fluorescent lamps are tube lights. So some tube lights are having long, so somewhat length, and the T5 lamps are short tube lights. So sometimes you observe this. There is long tube light and short tube light. So they are indicating the T12 and the T5 lamps. Then compact fluorescent lamps, CFL lamps. Then light emitting diodes, LEDs. Then we have mercury vapor lamps, sodium vapor lamps, halogen lamps, and others. And being an energy auditor, not only you are going to identify the areas where we have power consumption more, but we have to suggest the persons which kind of lamp we have to use. That is also an important issue. So we have to be updated ourselves regarding what kind of lamp we are going to suggest the persons where we have visited for auditing, and that lamp we have to know from top to bottom. So what are the positives and what are the negatives we have. Then only we can suggest the persons to go and acquire that particular lamp. Now coming to this domestic applications of lighting. So we are using generally fluorescent tubes, compact filament lamps, tube lights, such kind of things we are using. Nowadays, new lighting technology, it is replaced with the light emitting diodes. So which are 10 times more efficient when compared with this old incandescent lamps. So the temperature developed, the temperature rising because of the utilization of old incandescent lamps, that is more when compared with this CFL lamps. The efficient use of artificial lighting can provide energy as well as the cost savings also. That means as we are trying to concentrate more on this energy efficiency, definitely that is going to reduce the electricity bill. So we are going to save some portion of money regarding this issue. So here is the context of studying this particular light life cycle analysis. Now coming to this incandescent lamps, and it is consisting of some coiled coil, so which is made up of nichrome wire, and that is consisting of 8 to 10% of energy is utilized in production of light. So all these things we have seen in the previous presentation. Once again, just like a glance, I am trying to present all these cases. only 8 to 10% of energy is utilized for production of light, and remaining thing is going as a heat that is unnecessary for our power consumption point of view. Now coming to this fluorescent tubes. So here also we have lower wattage ratings to higher wattage ratings are available, and here we have certain amount of so because of their lower wattage lamps and are providing more lumens. So even it means the wattage rating of these lamps reduces, giving the same lumens output as of incandescent lamps. The objective is to provide maximum light output with minimal energy consumption. When it comes to these fluorescent tubes, they are available in different lengths, that is T5, T8, T12, and so on. And here it is have T12 lamps are the oldest and the most energy inefficient. So they have the largest tube diameter, also they are very heavy. Now coming to this T8 or T9 lamp, they are comparatively new and even have less tube diameter. Now coming to the other category, so these are more efficient when compared with the older ones. Now another category we have LED lamps. So these LED lamps are fitted into some housing. That means so these LED lamps are going to be provided with some housing so that these are going to be get provided some support. So that is mandatory. So these LEDs are somewhat expensive. So which is the biggest disadvantage. So just as a common man, we are going to look at the total initial investment we are going to keep on purchase of these LED lamps. Even though it appears to be somewhat high, but coming to this running period, they are consuming less amount of power and they are providing the desired level of illumination. So definitely these are going to be called as good for utilization of peripheral lighting purpose. So coming to this various types of parameters we are going to see in life cycle costing analysis. Now here is the context of life cycle analysis of the lamps we are going to see. As we are having domestic application, we are concentrating more on this domestic application. Now here we are going to see which is the best useful electrical lamp for the production of lighting. And coming this lumens, so just like a glance we will be seeing, so lumens. And here this is the light that is emitted from the source towards the work destination. There is a lumens. And watts, the total electrical power consumed by the lamp, that is called as the watts. Watt is rating. Luminous flux. So luminous flux is the factor used to describe the brightness of an area. This is called as luminous flux, which is expressed in terms of lumens. Luminous efficacy. Efficacy is different from efficiency. The luminous efficacy is the total luminous flux of the lux emitted by the light source per unit watt. And here we are taking how much amount of luminous flux that was liberated per watt of the electrical consumption. So luminous per watt is luminous efficacy. Then burning hours. So this burning hours is also indicating the lifetime. So in which lifetime of the lamp, how many hours this is working, that we are calling it as burning hours of this particular lamp. So this is also called as the life of the lamp. Then color rendering index. So this is called as CRI. This is a quantitative measure of the ability of a lamp to relate the color of various objects in comparison with an ideal source or natural light. So this is indicating so color rendering index. Suppose we are seeing some different colors when we are standing beneath one colored lamp. Suppose sodium vapor lamp, under sodium vapor lamp we are standing and our color is appearing to be yellow or orange. So mercury vapor lamp, we are standing below this mercury vapor lamp. It is going to show some white light along with a mixture of green and blue. So likewise, this color rendering index is also playing important role in deriving the total color index. Now this sodium vapor lamp, it has negative CRI, whereas the CFL lamps ranging about 50 to 90, the LEDs have CRI more than 80, color rendering index. Now coming to this comparison level, the keeping lumens almost constant around 2500 lumens, Comparison of various parameters of different lamps, it was shown by this table. Now look at this type of the lamp. Lumens almost we are going to keep that as same. Then corresponding what is rating and burning hours, the bulb cost in rupees. Look at this, the same luminous output. So incandescent lamp it is giving luminous output of 2600. Its wattage rating is 150 watts. Then burning hours is 1200 and the bulb is costing for 20 rupees. Whereas come to the CFL lamp, the lumens is 2600, the wattage rating is 50 watts, the burning hours is 8000, the bulb is costing for 700 rupees. CFL lamp. Suppose we have tube light of a finite length, that is small like T5. Luminous output is 2500. Wattage is 25 watts. Burning hours is 15,000 hours. Then the bulb is costing for 140 rupees. Then another length tube light, that is T8. Luminous output is 2500. Wattage rating is 36 watts. And working hours, the burning hours is 10,000 hours. And bulb is costing for 48 rupees. Then another kind of tube light which is having a normal length which we are utilizing in our house, that is a T12. The lumens is 2500, wattage is 40 watts and burning hours is 10,000 hours. The bulb costing for 45 rupees. And there exists a small decrement in T8 to T12. T8 is costing for 48 rupees. T12 is costing for 45 rupees. And the wattage rating of T8 is 36 watts for 48 rupees. And T12 is having a rating of watts 40 and the cost is 45. Then coming to this LED lamps is 25 watt and coming to this burning hours it is 50,000 and it is costing for 2,000 rupees. Now regarding this case, so here we are going to see the olden days technology incandescent lamp, it is going to be replaced with the LED lamp having a cost of 2000 rupees and same luminous output it is going to get. Then we are going to have the total, even though that initial investment it seems to be somewhat high, but coming to this running period, the power consumption is only 25 watt, so it is going to give less amount of energy bill. So likewise, here we can replace the olden days technology with the present new technology. So we can reduce the total amount of energy consumption and thereby we are having less amount of bill. And how to calculate this number of bulbs per cost. And here we can see the number of bulbs required for burning hours into cost of one bulb, that will give number of bulbs per cost. Now regarding this formula, here we have a fixed burning hours energy required. It can be calculated as energy required in kilowatt hours is equals to burning hours into rating in watts divided by 1000. So this is the formula we are using, the energy required in kilowatt hours. Then taking the local tariff into consideration, the cost of energy it can be calculated as by this formula, energy cost is equals to energy required into corresponding tariff. Finally, the life cycle costing is calculated by adding the bulb cost and energy cost, which is given as the life cycle cost is given, that is a combination of energy cost plus bulb cost. So likewise, here we can justify this life cycle costing analysis of electrical lamps. So here we can take LED lamps, these are having more number of burning hours, there's a peak one. The objective of this particular light source should have the maximum burning hours. So one time purchase, it has to cover large number of working hours. So here we can take, so 50,000 burning hours as reference. Within this we are calculating a particular magnitudes of all these life cycle costs of one particular lamp to the total lamps available. So it is tabulated in this table. So incandescent lamp, its burning hours is 1200. So for 50,000 hours of utilization, it requires 42 number of bulbs. Then the cost of these bulbs equals to 840 rupees. And for 50,000 hours of energy consumption, the total energy required is 50,000 into watts divided by 1000. So this is 7,500 kilowatt hours. Then energy cost is 38,625 rupees. So life cycle costing of incandescent bulbs is 39,465 rupees. Coming to this CFL lamp, compact fluorescent lamp, burning hours is 8,000 per bulb. In order to have 50,000 hours, the total number of bulbs required are 6 numbers. The cost of these 6 number bulbs is 4,200. For 50,000 hours of energy required, this is 2,500. So energy cost is 12,875 rupees. Therefore, life cycle costing of both total lamp cycle, which is 17,075 rupees. Coming to this tube light, which is having a different length when compared to the normal one. So T5 tube light, fluorescent tube. Burning hours is 15,000. In order to have 50,000 hours of operation, the number of bulbs required are 4. The cost of these bulbs of 4 is equal to 560 rupees. Then 50,000 hours of operation, energy required is 1250. Then energy cost is 6,438 rupees. The life cycle costing is 6,998 rupees. Then tube light T8, which is having a burning hours of 10,000 hours. In order to have 50,000 of hours operation, number of bulbs required is 5. They are costing for 240 rupees. Then for 50,000 hours of energy consumption requirement, that is 1800 units. Then energy cost is 9270 rupees. Then life cycle costing analysis of T8 tube light, that is 9510. Similarly, normal tube light we are using in our house, that is a T12 tube light. So burning hours is 10,000. For 50,000 hours of operation, number of bulbs required is 5 again. Coming to the cost of these 5 number of bulbs, 225 rupees. And for 50,000 of hours energy consumption, the required energy is 2,000. Then energy costing is 10,300. So life cycle costing is 10,525. Coming to this LED lamps. So burning hours is 50,000. So to have 50,000 hours of operation, number of bulbs required, that equals to 1. Cost of the bulb is 2,000 rupees. And for 50,000 hours of energy consumption, it requires units of 1250. So energy cost is 6,438 rupees. So life cycle costing analysis of light, that is given by LED lamps, that is 8,438. By looking at this particular comparison table, now it is clearly evident that the life cycle cost of LED lamp, that is very less when compared with this life cycle costing analysis of the other lamps, whereas especially incandescent lamp, it is taking 39,465 rupees, and CFL, that is 17,000, T5 6,900, T8 9,500, T12, that is 10,525. LED lamp is taking only 8,438 rupees. Now, by this comparison table, finally we can say that using LED lamps for our modern life, that is saving much more amount of energy as well as much more savings in electrical tariff. Now, this is showing the luminous efficiency of the light source, and the luminous efficacy is having improved, and a minimum power consumption and minimum life cycle cost. Now, coming to this star rating, now here we are going to concentrate on star rating also. So here is another context. Now, looking at this star rating, the devices which are having more stars, they are to be treated as excellent devices for energy utilization concept. Now, incandescent lamp, it is having 1 star rating, which is having a poor performance. CFL lamps, compact fluorescent lamps, they are having star rating of 2 star rating. Performance is somewhat satisfactory. T5 lamps, they have star rating of 5 star. Performance is excellent. T8 lamps, star rating is 4. Performance is very good. And T12 tube lights, they're having a star rating of 3, which are having a performance of good. Coming to these LED lamps, we have 5 star rating, and these are performing excellent, while energy consumption point of view, luminous efficiency, luminous efficacy, and overall energy saving and tariff point of view also. Now, here we can have the comparison between T5 and LED lamps in star rating. Even though the comparison between T5 and LED lamps, by the previous example what we have seen, T5 lamps they are having 6,998, that is a life cycle costing, and coming to this LED lamps 8,438. But here there exists a difference of 1,000 plus rupees, 1,000 plus. So T5 is to be treated as the best element for the utilization of light source. Now coming to this, the comparison of all these cases, here we are going to finally conclude that either we can use T5 fluorescent tubes or LED lamps for the production of light. And here life cycle costing of CFL lamp, that is somewhat high as compared with the remaining cases. The only advantages with LED lamps is that they have maximum burning hours when compared with the T5 tube light or T8 tube light, which are both coming to the comparison point. Now, here we have another advantage, and here LED lamps are installed. They don't need to be replaced again and again for years. The life cycle assessment shows that replacing older lamps of high power consumption and high cost, the new and innovative lamps of comparatively low power consumption and less cost should be beneficial for a particular application from the aspect of both energy and cost saving. So here is the concept where we have seen there exists a comparison among all the lamps available and the life cycle costing analysis of lights that are used. Because these lamps we are using, almost all houses, they are going to be switched on the lamps for 6 p.m. to 11 p.m. or 10 p.m. These are mandatory case for the total houses. So because of this reason, here we have included the concept of this life cycle costing analysis of lights. Now coming back to this life cycle analysis, the fundamental, here we are seeing the life cycle costing analysis we are handling this particular issue. Just it is a preliminary information. So extraction and processing of raw materials, then we are manufacturing, then it is getting packed, it is sent to the market, then use and reuse, these two things are maintenance of the product, then recycling and disposal of waste, then it is going to take an extraction and processing of raw material. Just it is a cyclic process. So it is going to repeat it like that. So it is having, so once we are using some elements, so they are going to be recycled after the discardal of these used elements. This is the principle. Then similar type of difference we have seen the production usages. Energy consumption and the quantity of light we are going to compare. Here, a 50 watt CFL lamp that is having production of 1.4 kilowatt hour energy consumption, and here this 60 watt GLS lamp, that is a tungsten filament lamp, that is 0.15 kilowatt hour. Coming to this usefulness 120 kilowatt hour, and this is having 60 kilowatt hour. So disposable, they are not at all using any energy, that's 0 kilowatt. The total is 121 kilowatt hour and 60 watt fluorescent incandescent lamp that is having 60 kilowatt hours. Coming to service hour, so this is having 7.2 million hours and this is 0.73 hours, million hours. Now coming to this production, energy consumption per million milli hours, that is 0.19 kilowatt hour and this is 0.21 kilowatt hour, and usage, that is 17 kilowatt hour we are going to use, 80 kilowatt hour that is done by this incandescent lamp. Disposable, both are having zeros. The total energy consumption, that is 17 kilowatt hour and 60 watt fluorescent tube that is consuming 82 kilowatt hour. Coming to this production of gases, carbon dioxide, sulfur dioxide, nitrous oxides, CH4, fly ash, mercury, and gaseous solid splits, and everything we are going to concentrate on that. Here we are going to have the production and usage 14.4 kgs of carbon dioxide. It is going to be released with the usage of 15 watt compact fluorescent lamp and a 60 watts incandescent lamp that is giving CO2 of 70 kgs. Now sulfur dioxide is 0.11 kg and for 60 watt incandescent lamp is taking 0.53 kgs. Now NOx, that is XPB2, 3, 4 like that, nitrous related issues is 0.07 kgs and this is giving 0.35 kgs. CH4 0.05 grams and this is 0.25 grams of methane it is going to produce. The fly ash is 0.82 and this is 0.82 kgs and this is 4.00 kgs. Mercury CFL lamp that is having 1 milligram and 60 watt GLS lamp it is having 4.86 milligrams. The gaseous and the solid split, it is 0.4 or 0.6, it is 1.94 or 2.9. After disposing these lamps, mercury is going to be have 0.69 milligrams and 60 watt lamp is not going to deliver any mercury contents. So solid waste 0.015 kgs and 60 watt incandescent lamp that's 0.042 kgs. So total mercury that is coming out from this CFL lamp disposal 1.69 milligrams and this is 4.86 milligrams. Total solid waste is 0.83 kgs and the incandescent lamp is having 4.04 kgs. Now by having a look on this comparison, clearly we can say that the CFL lamps, they are working normally for this working hours and they are having less amount of energy consumption and having a drawback of releasing mercury related issues while they are going to dispose. Now regarding this case, here we are going to see the total comparison. So here lamp energy consumption during life cycle, it is shown like this. So resources it is having 4%, production it has 5%, transport it is taking 3%, then use that is going to be used for 90% of its life, then disposable it is going to take as minus 2%. So this is the life cycle bar chart that is representing a lamp energy consumption. Then here we can see calculation of lighting energy. It is shown with the total amount of energy consumption is calculated as sigma PTF. So where is W is shown as energy consumption in kilowatt hours, which is equals to installed power P, that is in watts. Then T equals to annual burning hours H, and F is control factor, which is considering account of both the dimming and switch off periods. So both periods it is going to consider, either it is going to be switched off, either it is going to be dimmed. So both periods it is going to consider. So that is the total energy consumption expression. The average illuminance of the room, which is shown as illuminance E is equals to maintenance factor MF, that is multiplied with the utilization factor of the lamp, where N is the number of luminaires So number of bulbs what we have provided into luminous flux is 5, and A is the cross section area of the room. And this is the average luminance formula while we are considering the number of lamps. Whereas coming to this other formula, the lighting power density of a room that is given as P by A, that is given as luminance E divided by maintenance. Is the system luminous efficacy, the lamp illumination efficacy, it is going to be considered as a balanced losses also, which is expressed in terms of lumens per watt. So likewise, here we are going to calculate the power density, which is expressed in terms of watts per meter square, with the CFL lamp power density would be about 27 watts per meter square. So here we are having some comparison T5 lamps with the 90 lumens per watt and 500 lux, which is reaching the density of 15 watts per meter square, and CFL lamps are 27 watts per meter square. So by this comparison, we are going to say, so how the performance is going to differ from various types of luminous flux intensities. So luminous efficacy, which is taken on x-axis, and here corresponding power density expressed on y-axis. If you are going to plot these two for various kinds of lamps, incandescent lamps, it is occupying a luminous efficacy of between 0 to 20 lumens per watt, and CFL lamp, it is occupying between 40 to 60 lumens per watt. That is a compact fluorescent lamp. And see this T5 lamp, it is having a luminous watts between 80 to 100. That is power density watts per meter square. So this is the comparison range among this incandescent lamp, CFL lamps, and T5 lamps. Now, by this particular case, we are going to say the comparison among all these different luxes. If you are going to take 100 lux, so it is occupying between 0 to 10 and it's drastically decreasing. And after this particular 40th, it is coming towards 0. It is decreasing. All these waveforms, all these characteristics, they are trying to show exponentially decaying. But as the lux is increasing, they are going to stand among different types of power densities. So the least power density here, this incandescent lamp is, here it is appearing almost 0 to 10 watts per meter square. As the lux is going to increase, so they are changing their ranges from 0 to 20, then it is 40 to 60, and 80 to 100. So here we are taking another characteristics between utilization factor versus power density. If utilization factor we are going to concentrate, that is the point to 200. So 0% to 100%, we are going to concentrate on utilization factor eta versus power density watts per meter square. Then for utilization factor, so this is 0.9. That is showing the characteristic is getting the maintenance factor is for example 0.90 maintenance factor. Then utilization factor is reducing exponentially. If maintenance factor is 0.75, then we have the maintenance factor 0.75 is showing the percentage utilization factor is also reducing, but it is having somewhat more power density watts per meter square. If maintenance factor is 0.5, then the power density watts per meter square, that is also having somewhat shifted up when compared with the remaining two utilization curves. that is starting with 40 and falling up to 15 watts per meter square. So like that, we are going to concentrate on different issues. Then coming to this normal power density. So normal power density is also to be concentrated. So normal power density is total system power divided by the maintained luminous flux on the workspace into watts per meter square into 100 by this x, where that is going to be replaced with 100 by maintenance factor into utilization luminous flux in the room, then light output ratio that is multiplied with the lamp efficiency and the gear system efficiency. And here we are going to take, according to the scientist which is Hasmiller, it has shown in 2007, the targeting values of luminous lighting installations are efficiency of the gear system should be greater than 84%, and efficiency of the lamp should be greater than 70 lumens per watt. Then LO or light output ratio it should be greater than 0.75, and the maintenance factor should be greater than 0.75. Then utilization luminous flux in front of in the terms of luminous, the luminous flux is greater than 2 by 1 plus 0.5 into ANTA divided by ATA, where ATA is the task area and ANTA is total non-task area. So within one particular room, the light is going to be focused on the workspace. Suppose the reading table is there, and there we are going to concentrate the total light which is going to be fallen on the reading table alone. There is a reading lamp. Suppose we are going to consider the total room that is going to be taken as ANTA. There is a total room. Within that, we are going to concentrate the total light to be fallen on the task area ANTA. And coming to this cost, initial cost of this lamp, capital recovery factor, that is annual cost of the initial investment, CI equals to I into small I of 1 plus small I whole power n divided by 1 plus small I whole power n minus 1. Minus 1. So this capital I is investment cost and capital CI is annual cost of the initial investment, and small I is interest rate, I equals to P divided by 100. P is the interest rate in percentage, where N is number of years. So variable cost, we are going to concentrate on this service, that is CE. So energy costs are calculated by multiplying the total power of the lighting installation by annual burning hours and the price of the electricity. So here we are going to take, so CE is energy cost in rupees as per our India is considered, and the number of the luminous is NLU. Then CE is the price of electricity, so rupees per kilowatt hours. P is annual burning hours, that is in hours. Then P is power of the luminaire, that is taken in terms of watts. Now the lamp cost CL is calculated NL eta L CL into T by TLL into 1 plus K. Now CL is annual lamp cost, eta L is number of lamps, then CL is price of the lamps as per India it is in rupees, P is burning hours in hours, then TLL lamp life cycle, that is expressed in terms of hours. That is expressed in K is average mortality during lamp group replacement method expressed in terms of percentages. And likewise, here we have so many formulas to be taken. Then coming to this service cost of the lamp life, that is CC is equals to eta L into CC plus CM by TC, where CC is annual clearing cost, that is in rupees. NL is number of lamps required. CC is work cost of clearing the lamp, that is in rupees as per India. And CM is material cost of clearing per lamp, that is rupees as per Indian calculation. And TC is the clearing period in years. Now coming to this calculation, here we are going to see different lamps, how they are going to differ in their performance. Price of electricity, so rupees per kilowatt hour. So this is incandescent lamps, that is 15, fluorescent lamps, CFL lamp 1, CFL lamp 2, different categories, 15 each. LED lamp 1 and LED lamp 2, they are having 15 each. The power of the lamp is tungsten filament lamp 60 watts, CFL 1, CFL 2 and LED 1, they are occupying 15 watts and LED is taking 10 watts. The price of the lamp in pounds, actually it was shown in terms of pound British units, that is 0.5 pounds, and CFL lamp is 5, CFL lamp 2 is 10, LED 1 is 20, and LED 2 is 50. Then coming to the lamp, so annual burning hours, coming to this, it is 2000, next CFL 1 2000, 2000, 2000, and 2000. Coming to the life of the lamp, which is 1000, then another lamp is consisting of 6,000 hours, then CFL lamp 2 12,000 hours, LED lamp 1 20,000 hours, and LED 2 type category is having a life of 50,000 hours. Then coming to this zeros, the interest rate is 0.05 for all these lamps categories. Then coming to the service life, the number of years is this ordinary tungsten filament lamp is taking 1 hour, 1 year, and CFL lamp 1, CFL lamp 2, they are considered. CFL lamp 1 is 3, CFL lamp 2 and LED 1, LED 2 lamps type, they are occupying only 5 number of years. So there is more. Coming to this, calculate the values of these lamps 0.53, 1.84, 2.31, 4.62, and 11.55. Coming to this energy costs, it is 80 for GSL lamp, that is in pounds. Then CFL 4.5, 4.5, 4.5 each. Then LED lamp at $3.3 as per this British calculations are considered. So that we can convert these values into our Indian currency. So lamp is costing GSL lamp, there is 1.05 pounds, and CFL lamp 1.84 pounds, CFL lamp 2.31. Then LED 1 is costing for 4.62, and LED 2 it is costing for 11.55 pounds. Convert everything into equivalent Indian rupees. Now coming to this burning hours versus lamp energy costs, that is showing if the burning hours are increasing, definitely the lamp and energy costs are going to increase. For example, we are taking incandescent lamp that is having 0 burning hours to 4,000 burning hours. The energy cost that is going to increase linearly. So, as per this, burning hours are increasing, lamp cost as well as the total energy cost is increasing proportionately linearly. Whereas come to this CFL lamp 1 and CFL lamp 2 categories, they are slightly varying their lamp and energy costs when compared with this burning hours increase. Then LED lamp 1 that is having, so it was shown LED lamp 1 energy consumption cost is shown here, and LED lamp 2 that is having lamp and energy cost that is starting with 10 pounds above, it is going to increase linearly like this. So out of this case, CFL lamps that is occupying low energy consumptions. So this is LED 1 and this is LED 2, and this bottom one is CFL lamp. Then coming to this lamp type and lamp energy costs, we are going to compare. So GSL lamp, that is incandescent lamp, that is having energy consumption costs up to this is blue colored one, the greenish blue, and lamp costing is shown as yellow. CFL 1 type category, energy consumption is shown with this greenish blue, then lamp cost is shown in yellow. So correspondingly CFL 2, LED 1, LED 2. So all these things we are trying to show in this bar chart as per this case. Then coming to this luminous flux and lifetime. As the lifetime is increasing, automatically the luminous flux that was delivered by any element, it is going to get reduced. Now here we can say that the life and the efficiency of any electrical device, if it is going to work for some number of hours, then its efficiency is going to reduce. That is shown by this characteristics. Then Here, if you are trying to see some calculation, if you are trying to see this, the required illuminance is 1000 lux within this room. The dimension of this particular room is given as 4 by 5 meters, that is 20 meters square area. Then efficiency theta is 0.6. Then we have the maintenance factor of 0.67. The time of operation is 3000 hours. The lamp type, they are given it as HCI 35 watts, that is delivering 3500 lumens. The power rating of this lamp is 40 watts, which is having 87.5 lumens per watt. Luminous efficacy is given as 87.5 lumens per watt. Now, how to arrange this case? So, luminous flux pi equals to EA by zeta into maintenance factor. So, that is giving 49.8 kilo lumens. Then, for 3000 hours of operation, how much lumens are required? That is 149, that is 49.8 to 10 power 3 multiplied with 3000. So, that is given 149 into 10 power 6 lumen hours. Then power consumption P equals to 49.8 into 10 power 3 lumens by 87.5 lumens per watt. So that is giving 569 watts rating of the lamp, which is having 28 watts per meter square. Therefore, for 3000 hours of operation, the watt is required is 28 watts per meter square. That is going to be multiplied with this 3000 hours. That is going to show 3000 hours into 569, that is 1700 kilowatt hour. We are going to express in terms of area of this building, that is 85 kilowatt hours per meter square. Therefore, installation cost is given as 100 pounds per meter square. Then energy consumption is 85 kilowatt hour per meter square. The cost of electrical energy, suppose we are going to take 0.15 cents per kilowatt hour, there is a cost of power consumption. So electricity power consumption cost is 12.75 pounds per meter square. Then for 10 years of utilization of this particular lamp, then the total cost of electricity is 127 pounds per meter square. So like that, here we can calculate the maintenance as well as the re-lamping costs. We can calculate by these methods. And coming to this another category, the distribution cost of lighting during its life cycle of an installation. Here we are going to have some comparison. So installation charge is 24%, the electricity consumption charges is 43%, and the maintenance charge is only 33%. For 1% increase in electricity. Whereas come to this 5% increase in the power consumption, here we can take installation charge is now 20%. Then electricity utilization is now 52%, and the maintenance charge is now 28%. So 5% increase in electricity, that is going to increase the energy consumption charges. Previously, that is 1% increase in electricity, that is only 43%. If 5% is increased, it is 50%. Then coming to this office lighting purpose, suppose how to calculate the lighting requirement for the office. Here we can see the energy efficient office we are going to design. That means all existing lamps we are trying to replace them. The low power density is taken into consideration. The required illuminance is 500 lux. Then dimension is given as 5 meters by 4 meters, which is 20 meters square. The efficiency of the system is 0.7. Maintenance factor is 0.67. And the time of operation of these lamps is 2000 hours. And lamp type here we are using is L. So LFL, that is a 54 watts, which is delivering 4450 lumens, 4450 lumens it is delivering. The power rating of this system is 58 watts. which is 77 lumens per watt. Now here we can calculate the total luminous flux required is E into A divided by eta into maintenance factor. So from that we have calculated 21 into 10 power 3 lumens. Then hours of operation is 2000 hours. So according to that, the lumen hours is 42 into 10 power 6 lumen hours. Then the power rating of this lamps required is 21,000 lumens divided by 77 lumens per watt. That is giving 270 watts of the lamp rating, which is nothing but 13.5 watts per meter square. So for 2000 hours of operation, so the rating of the lamp, that is energy consumption we are going to take, that is 270 into 2000 hours, that is 540 into 10 power 3 kilowatt hours. Now we are going to express in terms of meter square of the area of this office, which is 27 into 10 power 3 watt hours per meter square. Then initial cost is 31 pounds per meter square. That is the installation charges. Then energy consumption charges are 27 kilowatt hour per meter square energy consumption within this area. And cost of electricity, if you are going to take per unit of energy consumption, it is charged with 0.15 pounds. Then for total energy consumption, the cost of electricity is now 4.05 pounds per meter square. And cost per electricity for 10 years is 40 pounds per meter square. So like that we have calculated one thing. Then coming to this life cycle costing with the maintenance costs, we are going to concentrate. The total life cycle is 24 years, for example. The maintenance interval is 6 years. So for each 6 years, we are going to maintain this particular lamps activity. Now, here we can take the maintenance interval, which is 6 years once. So NP equals to 4. 24 by 6, which is equals to 4. The maintenance cost is 5 pounds per meter square. Interest rate is 6%. Then electricity cost is 4.05 pounds per meter square. Then electricity price increases by 1% or 5%. So here we have to calculate the present values of the total life cost is. Now installation charges is 31 pounds per meter square. Electricity charges are 56 pounds per meter square, 1% annual increase. Then electricity charges, that is 82 pounds per meter square for 5% annual increase. And maintenance charges, that is 20 pounds per meter square, no annual increase. Now these calculations, everything we have done by this methodology. So here is one example we have already come across, and we have taken the same methodology for the calculation of this particular example. Now we will be showing the percentage decrease. The percentage decrease in the installation charges. Now electrical consumption charges, it is shown previously 52, now this is 62%. Now here we have maintenance charges of 19% previously. Now here we have a maintenance charges of 15% after the lamps has been replaced. Now here we are going to conclude from this example the life cycle costing analysis, because realization of lamps for the generation of artificial light, which is day by day issue. So we should not avoid, we are unable to avoid the utilization of the lamps for power generation, power consumption. So the number of lamps we are going to utilize, they have to be replaced with some latest to modern technology lamps, so that even though initial charges they seems to be somewhat high, but the total amount of running charges they are going to be reduced. So olden days technology has to be replaced, and it has to be replaced with a newer days technologies. This is about life cycle costing of lighting process. And finally we have return on investment. We are looking at this return on investment. So what is meant by return on investment? So what exactly we are going to talk about this? If you are looking this return on investment, so this is nothing but Return on investment ROI, which is called as the measure that investigates the amount of additional profits produced due to a certain investment. Just we are going to put some initial investment. After the process was run and it is going to deliver some output and it was sold in the market, finally it is going to give some cash inflows which are positives. That we are going to call them as that is the return on investment. Something what we are spending, we are going to gain back. The business uses this calculation to compare different scenarios for investments to see which will produce the greatest profit and the benefit of the company. And we are having more amount of rate of investment, then we are going to call it as profit. And if you are going to have a return on investment, then it is no return. That is called as negative cash flow. That means we are having losses. And here this particular rate of investment, return on investment, this is going to be taken in purchase of a car, buying a computer, pay for colleges and extra. So here we are going to see various applications of this return on investment. Coming this simple rate of return of investment, return on investment formula, it is shown as gain from investment minus cost of investment divided by cost of investment into 100. So this is shown as return on investment percent. So this is the formula. Suppose we will see a small example. Now gain is $5,35,000. The cost is $4,00,000. What is the rate return on investment? So we have invested capital amount of 4 lakhs rupees, 4 lakhs dollars, and we are having a gain of $5,35,000. Then what is return on investment? That is total gain 5,35,000 minus initial investment, that is 4 lakhs dollars, divided by initial investment 4 lakhs dollars, which is given as 34%. So for this simple example, return on investment is 34%. And another example we will see, gain is $3,640 and capital investment is $1,880. And what is return on investment? That is 94%. So we got return as $3,640 minus investment is $1,880 divided by $1,880, which is equals to 94%. So like that we can calculate simple return on investment. Let us come to this another example. Suppose a car was purchased for $26,450. Because now we have some reliable transportation, we are able to obtain a job and earning dollars of $10,860 in your first year. Calculate your return on investment for that year. Which is also simple. So here we have earn of $10,860 and we have initial investment of $26,450. So we are earning only $10,860, but we have invested $26,450. But we are earning less compared with our capital investment. So return on investment is the earning is 10,860 minus the capital amount we have kept is 26,450 divided by 26,450, which is minus 0.59 into 100, that is 59%. This purchase, the company being earning $50,000 per year. Find return on investment for the first year. So here we have purchased for $5 lakhs, but we are getting only $50,000. So 50,000 minus $5 lakhs divided by $5 lakhs, which is having minus 90%. So we have a loss for the first year, that is only 90% we have acquired. So what is meant by this negative return on investment? This is nothing but a step back and think about a different question. So what would it means we had a zero return on investment? This is only occurs when the numerator after our formula is zero. And this can only happen if your gains were the same as our costs. This is meaning we broke even. So this return on investment is negative. The cost must be greater than the gain, or we have yet to achieve the amount of the gain greater enough to cover the cost of investment. Simply, we are going to tell that if return on investment is positive, we have gain. If return on investment is negative, we have loss. So these are the two simple landmarks we are going to see. Return on investment is positive, we have gains or we have profits. If return on investment is negative, we are in loss. Still, we have to acquire the more amount of money in order to meet the capital investment what we have invested. Now, coming to this investment that is related to time. Then take some business in the problem 4. Here he has invested $50,000. For the first year, he got $50,000 for first year. Then what is the return on investment? For the first year, return on investment for the end of the first year, he got only $50,000. So what is the return on investment for first year? That is $50,000 minus 5 lakhs investment divided by 5 lakhs investment. 5 lakhs investment. So that is to be taken. Here, return on investment for the first year is 90%, which is minus. Then second year, return on investment, so 50,000 plus 50,000, it is 1 lakh. So 1 lakh minus 50,000, 1 lakh minus 5 lakhs by 5 lakhs, which is minus 80%. Return on investment is minus 80%. Then return on investment for third year, which is the cumulative of 50,000 in 30 years, that is 1,50,000 minus 5 lakh, 1,50,000 minus 5 lakhs by 5 lakhs, that is minus 70% return on investment at the end of third year. Then at the end of fourth year, return on investment is 2 lakhs minus 5 lakhs by 5 lakhs, which is minus 60%. Then here we are having year by year, we are going to have a reduction in the loss. So that means at the end of the fourth year, we have a loss of only 60%. So like that, the time involves in this return on investment issue. So the total loss, what was incurred year by year, it is going to get reduced. So loss is getting minimized. So loss is being reduced. Now, if you're going to concentrate on calculate a rate of return on interest, return on investment for each consecutive year until you obtain the positive return on this investment. Suppose example 3. So here he has purchased a car for $26,450, and 1 year he has earned $10,860. By how many years of his service he will be getting positive gains? So return on investment first year, which is $10,860 for first year, minus investment is 26,450 divided by 26,450. It has a loss of minus 59%. So return on investment is only minus 59%. At the second year, cumulatively we got some amount 10,860 into 21,720. Minus 26,450 divided by 26,450, which is having return on investment at the end of second year is minus 18%. Suppose we are calculating for third year return on investment, for third year 3 into 10,860, which is 32,580, minus capital cost is 26,450 by 26,450, which is return on investment at the end of third year is 23%. That means, for this example, if he is serving for 3 years with an annual return of 10,860 for 3 years, he is going to have positive returns on his investment. So return on investment is becoming positive. That is profit. And in different scenarios here we are going to see, suppose a crash with your car in a problem of 3 and you need to purchase a new one. And there you have two choices. First, car A is worth $19,345. So, since gas would cost you about the same as for the old car, you would still be pocketing about $10,860 per year. Initial investment of car A is $19,345, and at the end of each year, you are having $10,860 per year. Coming to this car B, that is $27,120, and but it is extremely good on the gas mileage. So after paying for gas, you will be costing up $13,430. Just fuel charges we are going to subtract, then we are going to get $13,430 per year. So which car you are going to buy, and at how many years of service you will be having positive rate, positive return on investment. So car A for the first year, return on investment. First year ending, you have bagged 10,860 rupees. 10,860 minus car A initial investment is 19,346. So here we have the return on investment of car A first year is minus 44%. Coming to the second year, return on investment of car A, that is 12%. That means after running for 2 years of your car A, you are capable to convert your loss into profit of 12%. Coming to this car B, return on investment. First year, car B is bagging $13,430 with the initial investment of $27,120 divided by 27,120. You are having the return on investment for car B first year is minus 50%. Still you are in loss. Then return on investment of car B for second year, that is 26,860 minus 27,120 by 27,120, which is equals to minus 1%. So by this return on investment, you will be having second year for car B, you are having return that is also still loss, minus 1%. Return on investment for car B at third year, that is you bagged $40,290 minus investment is $27,120 divided by $27,120, which is equals to 49%, which is positive. So at the end of third year, car B, it is going to have a gain of 49%. So you are moving into profits when compared with the losses. So like that, we are going to calculate some relevant information regarding this return on investment. So these problems are to be exercised with some more examples so that you will be having familiarity with this return on investment. So like that, now finally we are going to conclude this particular chapter in this form, so being an energy auditor. So as a title, what we are having, energy audit, conservation and management. So frequently we have to audit, we have to inspect the total residential areas. It may be industries, it may be factories, whatever it may be. They have to be periodically inspected to suggest some remedial actions where we have some losses. And the lossy areas has to be identified, and we have to tell the corresponding operating persons to take some necessary actions to reduce the losses in those areas so that the losses are getting minimized and the total power consumption charges are going to reduce and the total bill is going to come down. Then auditing we have done. Then conservation. So conservation means the areas where we are going to see. So here we are suggesting the existing equipment has to be replaced with the new equipment where the modernization technologies are going to be involved so that the losses within that equipment is going to be reduced because of the nowadays modern technologies are available. Now here the conservation we are going to take into consideration. So the energy which we are going to use in the form of more energy utilization, has to be replaced with the new devices which are consuming low amount of power without disturbing the luminous output and the working efficiencies of the machines. So like that, we are going to conserve some amount of energy from misutilization or from the losses. Then management. So here we are going to see which areas are going to have much more amount of power consumptions, where the energy is getting wastage, and there we are going to suggest some remedial actions. This has to be replaced by this one. So how far this particular how far this particular machine or the equipment is more useful when compared with the old equipment that is already in service. So whether the lifetime is available with this element, the new element what we are going to replace with the existing one. Now we have to be in a position that if the questions raised by the persons where we have gone for auditing, those we have to give some instructions. So by these points, the existing equipment has to be replaced. Now, what are the plus points of the new equipment we are going to replace with the old one? That also we are having some familiarity within this new equipment, the latest technology. They have to move in the direction of energy conservation, less power consumption, so that the natural resources like coal, water, gas, oil, whatever it may be, they are going to consume less. And we have to search for other alternatives also in order to save energy for the upcoming near future generation. So, for your convenience, I have provided all these topics as a running notes for your verification once again. If it is just a lecture without having any presence for your visualization, so everything it is just for listening purpose. And here each and every topic, each and every chapter, here I have provided a running notes like a visual representation as well as a hearing representation. So I hope this visual representation will help you in reviewing the total concepts what we have come across this particular energy audit, conservation and management. So thank you for your support for giving me a chance for delivering lecture on this energy audit, conservation and management. Thank you once again.